Hi class, welcome to exercise 2C, where we're going to be investigating parallelograms using congruence. In this lesson, example 5 will be proving properties of quadrilaterals. And your pre-learning for that will be question 1 in the new book and question 4 in the old book. And then we do example 6, which is testing for a type of quadrilateral. And your pre-learning for this example is question 4 in the new book and question 7 in the old book. And just as we left off in the last lesson talking about the power of deduction, we have to take it to a new level in this lesson. So if you're not comfortable with tests for congruent triangles and their properties, then you need to work on the previous lesson. Alright, I'll see you in the introduction. Parallelograms are like a family of shapes, so let's define them in a diagram that is something like a family tree. This will make it clearer that they are like children of the previous ones by containing all of the same conditions but adding some more. But before we do this, let's recall that we've defined how we note two lines are parallel and how we note if two lines are perpendicular. We now have a new concept to add called bisection. Now we say that CD bisects AB if the intersection of the two lines splits AB perfectly in half. So for example, in this diagram of these two lines intersecting, if we mark in the point R, then AR is equal to RB if CD bisects AB. Unlike for parallel and perpendicular, there's no fancy symbol for this, we just say it. So remember the term bisect, as in bi for two and sect for cut off or section. Anyhow, with that, let's move on and have a look at the parallel family tree, which I've already written out. So the first generation is a parallelogram, which is just a quadrilateral where the opposite sides are parallel with each other. And properties that we'll find in the parallelogram are that its opposite sides are of equal length, the opposite angles are equal, and let me just turn this parallelogram white because the colours are starting to get a bit confusing. I hope that helps. And the last property is that the diagonals bisect each other. So by bisecting each other, it means that one side of the diagonal is the same side as the other one. And that's obviously true for both of them. Now, if you're presented with a shape and you want to test that it's a parallelogram, well, if both pairs of opposite sides are of equal length, then it's a parallelogram. If the opposite angles inside the quadrilateral are equal, then it's a parallelogram. And if the diagonals bisect each other, then it's a parallelogram. There's one other test that's not one of the properties, and that is if just one pair of the sides are parallel and equal. Okay, and then from the parallelogram, we have two of the next generation, the rhombus and the rectangle. Now the rhombus is just a parallelogram where all the sides are of equal length. And a rectangle is a parallelogram where all the interior angles are 90 degrees. And let's just slide it up here to see the properties and the tests for these two shapes. So as stated by its definition, the rhombus has all sides at equal length. And a property that it inherits from all parallelograms is that the opposite angles are equal. And just like all parallelograms, the diagonals bisect each other, but in a parallelogram, they do so at right angles. The other things that a rhombus does is that the diagonals bisect the interior angles. So for example, this angle here, the diagonal will be cutting straight through the middle of it and split it in half. Okay, let's look over at the rectangle, and the properties for this are that opposite sides are of equal length. Now obviously that comes from our parallelograms, but the difference here with other parallelograms is that all angles are 90 degrees. And the diagonals are of equal length and bisect each other. And that means that either half would be the same length as the other half. And the tests to ensure that we have a rhombus are that all sides are of equal length and that the diagonals bisect each other at right angles. And for rectangles, the tests are that all angles are 90 degrees, or the diagonals are of equal length and bisect each other. And the final generation of our family tree is the square. And even though the square might be something that you've defined as its own thing in the past, it really is just a rhombus that is also a rectangle. So it will inherit all of those properties. And that is that all sides are of equal length, all angles are 90 degrees, diagonals are of equal length and bisect each other at right angles, and that the diagonals bisect the interior angles. And the way to test if we have a square are that all sides are equal and one angle is 90 degrees, or that diagonals are equal in length and bisect each other at right angles. That should be obvious that the diagonals equal length is what we get from a rectangle, and the bisecting each other at right angles is what we get from the rhombus. However, I'm not sure if my wonderful drawing here or explaining here has enlightened you too much, and of course you can read a lot of that in the textbook. So let's pop over to GeoGebra and have a look at it, which you can come and play with yourself if you follow this link. Here we have an ordinary parallelogram, and notice how the opposite angles are equal and the same colour. But also notice that the diagonals do not bisect these angles. But if I use a slider to make these sides the same length, now the diagonals bisect the angles. So this is obviously a rhombus. If I move this slider, we now make the interior angles 90 degrees. So this is obviously a square. Let's return to the original parallelogram and rotate these angles so they're 90 degrees again. So we now have a rectangle. Then once we extend the size of the smallest side, we make all the sides the same length, which is a square. This demonstrates that there's two paths on our family tree from parallelogram to square. You can look at the square as either a rectangle with equal sides or a rhombus with all angles 90 degrees. We'll look at one last thing before we go back to the OneNote, and that's the length of the diagonals and their angles at their intersection. Starting with the parallelogram, we can see that both sides of one bisector is 1.83, and for the other diagonal it is 3.91. Now if we turn this into a rectangle, we can see that diagonals all become the same length. Then as we turn it into a square, we can see the diagonals are perpendicular. Also note that the diagonals are still the same length. Now let's turn this square into a rhombus, where we can see that the diagonals are still perpendicular, but now they're different lengths. We have a 2.35 here and a 4.41 on the other one. Using this little GeoGebra applet, we can see that diagonals bisect each other for all parallelograms. If the two sets of parallel lines are perpendicular, then the diagonals are the same length. If all four sides are the same length, then the diagonals are perpendicular. So there's some beautiful symmetry to all that. Okay, back in the OneNote here. While we've demonstrated what the properties of these different parallelograms we're learning about are, I have not proved them. And that's because I'm not going to do that here. The point of this lesson is teaching you how to. So in the following sections, we're going to use some geometric rules and laws that we've already covered to prove these rules. And as I've stated in the previous lesson, this is the underpinnings of mathematics. One mathematician creates or discovers an object and defines all the rules that are involved with this object. Then later on, they, or another mathematician, will extend these rules to understand, explore, define other objects. Anyhow, it might be a good idea to pause the video now and work on these building understanding questions in the new book. And that's equivalent to questions 1, 2, or 3 in the old book. Alright, I'm going to see you in the next section. In this section, the quadrilaterals we're working with are parallelograms. So to prove the properties of parallelograms, we will need to use congruence and the parallel postulate. And let me copy this from our lesson where we reviewed the laws of geometry. So we can recall that alternate angles are equal, corresponding angles are equal, and co-interior angles are supplementary, or in other words, sum to 180 degrees. Also recall the 4 conditions of congruence. The first one is SSS, and that states that two triangles are congruent when all 3 sides have a corresponding side of the same length. And rule 2 is SAS, where a triangle has 2 corresponding sides with a corresponding angle. And the third one is AAS, which is 2 corresponding angles and 1 side. And finally we have RHS, which is when we got a right angle triangle with the same hypotenuse and 1 other equal side. When applying these rules, we need to break down the parallelograms using its definitions. This will often involve drawing the parallelogram and remembering the definitions. Anyhow, let's use these skills and start with our first example of proving some properties in example 5. So in part A, We're asked to prove that a parallelogram has equal opposite sides. Let's start by drawing a parallelogram that is defined by the opposite sides being parallel. And let's mark in its corners as points A, B, C, and D. Now let's draw a diagonal line from A to C. Now if I copy and paste this parallelogram over here and delete these two lines, then we can see that these two angles are alternate angles. And if I paste that parallelogram one more time, and then delete these two lines, we can see that these two angles are alternating angles. So I could now redraw this parallelogram as two triangles and mark in the angles we found with the alternating angles. And because the angle BCA is equal to the angle DAC, in this case we've marked it as X, and the angle BAC is equal to the angle DCA, which we've called Y in this case. And both triangles share the side AC, then we can see we have angle, side the same. So therefore these triangles are congruent by AAS. And when we talk about corresponding sides and corresponding angles, we can see that the side that touches the angle Y is AB in one and DC in the other. So AB has to equal DC. And in the other triangle, AD and BC both touch the angle X, so they're the corresponding side. So AD is equal to BC. So we've shown that opposite sides are equal to each other by just using congruence and the parallel postulate. So now you know for sure that this rule is true. Alright, let's try part B, where we use the fact that we just found, opposite sides of parallelograms are equal, to prove that the lengths of a diagonal in a rectangle are equal. And this is a perfect example of how one discovery can lead to another. Okay, let's recall the definition of a rectangle is any parallelogram where all the angles are 90 degrees. So let's draw a rectangle with all the angles 90 degrees and mark in the points A, B, C, and D. And because a parallelogram's opposite sides are the same, BC has to equal AD and AB is equal to CD. And now let's draw in the diagonals. And if we look closely, we can see two triangles in this rectangle, ABD and ADC. And let's mark in the side lengths and angles we've already got. So now we've got two sides with the same length and the same angle between them. So by SAS, the triangle ABD is congruent to the triangle ACD. And so that means all angles are the same and all side lengths are the same. So the corresponding side BD has to be equal to AC. And so the diagonals are equal. Isn't that cool? Alright, pause the video, question 1 in the new book and question 4 in the old book. This is your chance to have a go at these sorts of things. But before you go, make sure you draw down what you need to explore the shape you're going to work on. Then work with the facts that you've been given about its properties. And I'll see you when you come back in the next section. In the last section, we're given the definition of parallelograms and then we had to prove their properties. But in this section, we're going to be given the properties of a shape and then use these properties to figure out what the definition of the shape is. This means that there's a two-way relationship between the definition and their properties. Alright, let's try this out in example 6, where we're going to prove that if opposite sides of a quadrilateral are equal, then it has to be a parallelogram. Alright, let's start by drawing a quadrilateral that has two equal length pairs of opposite sides. And now let's draw in a diagonal which creates two triangles. Now let's highlight those by drawing them separately here. And as you can see, I've marked in the same points. Now because AB is equal to DC and BC is equal to AD and they share the diagonal, therefore all sides are the same length. So by SSS, the triangle ABC is congruent to the triangle ADC. And this means that the corresponding angles are equal. So the angle ACA is equal to the angle DAC. And therefore using alternate angles, AD has to be parallel with BC. And similarly, the angle BAC is equal to the angle DCA. And once again, by alternate angles, AB is parallel to DC. Therefore, both pairs of opposite sides are parallel, so this is a parallelogram. We already know that a parallelogram implies that opposite sides are equal, but now we know that opposite sides being equal in a quadrilateral proves that it's a parallelogram. So this is a great example of the two-way relationship. All right, let's move on to part B, where we're asked to prove that if the diagonals of a quadrilateral bisect each other at right angles, then it's a rhombus. Note that I've said bisect, so let's draw these diagonals first. Okay, so see how they go the same length from the point at the middle? So now if we draw these lines to make a quadrilateral and mark in the points, and let's mark in these right angles and the point R. So we now have 4 triangles that have 2 sides the same, i.e. the orange or the blue ones, and the same 90-degree angle between them. And this means that they are congruent by the SAS rule. And because they're congruent, all the sides are the same length, right? Or all the corresponding sides. So these outside lines, like A to B, B to C, D to C, A to D, will all be the same length. So once again, we can see that a property of a rhombus has this two-way relationship as well. Okay, so it's your turn. Let's pause and work on question 4 in the new book and question 7 in the old book. And then I'll see you when you come back for the summary. Okay, welcome to the summary. I just want you to be clear that this sort of reasoning and discovery requires that you're very clear about the definitions given to you in the questions. By the end of this lesson, you will or should be able to see the connections between the properties and the tests of quadrilaterals. And that means that a successful student will review the properties of different types of parallelograms, know what is required to prove various properties of parallelograms, understand that showing 2 triangles are congruent can help prove that other angles and lengths are equal, or that lines must be parallel or perpendicular. And finally, be able to use congruence to prove properties of quadrilaterals or test for types of quadrilaterals. Alright, so I'll see you in the next class or the next video. See ya.